أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم فبأي آلاء ربكما تكذبان. Thanks to Allah subhanahu wa ta'ala for all his blessings and bounties that he has bestowed upon us. Today is 29th of July 2020 and still we are talking about partial differential equations. If you remember from the previous lectures, we got an idea about partial differential equations. We found there about the different types of equations are there. Number 172. So try to mute your microphone once you come in. Okay, I do it. So we got an idea about different types of partial differential equations. How do we look into the solution? There are quite a few different channels are there. Sometimes we see that yes, it's a partial differential equation, but could be handled just like the techniques available for handling ordinary differential equations. Nevertheless, it's a partial or ordinary, it is a derivative. So in order to kill the effect of derivative, we have to look into the reverse process of integration. So sometimes it's another viable option that straight away you just go and then integrate the given differential equation as many times as the order of the equation is there, and we obtain the solution. There is one very prominent technique available in the literature to find the solution of partial differential equations, which is closely resembled with variable separable form, the form that we have discussed while talking about first order ordinary differential equation. The very basic, the very starting technique to simplify ordinary differential equations is known as variable separable form. So pretty much on the same lines, we can also look into the method of separation of variables. So from the title, separation of variables, we can imagine behind the scene what is going to happen. So we are going to separate variables, of course, but in slightly different way. It's not exactly the same thing as we have done with ordinary differential equations, because now, of course, we are talking about entirely different mathematical formulation of physical phenomena in the form of partial differential equation with multiple independent variables, more than one. So idea is there, but the implementation is slightly different from the one that we discussed while talking about first order ordinary differential equations. So what is the description behind the scene? What is the message behind the scene? We say that in this particular method, the method of separation of variables, it is assumed that the solution, what the solution is, of course, this is going to be a relation between dependent and independent variable. So we generally, or we try to write it down in the most compact and composed form when the dependent variable is expressed as a function of independent variables. This is going to be the solution with certain criterion behind the scene to satisfy the given differential equation involving dependent variable and its derivatives identically. Of course, definition is there. Solution is there. Solution means the value as an expression of the dependent variable. We see that it is assumed that the solution, that is the dependent variable, can be expressed as a product of unknown functions, each of which depends upon only one of the independent variables. So message is it. In this technique, the dependent variable is going to be expressed as a product of unknown functions. No, it depends upon the number of independent variables. We are going to introduce unknown functions, and the product of those functions is going to describe eventually the solution of the given partial differential equation. With this solution, the partial differential equation can be expressed in such a way that one side depends upon only one variable, while the other side purely depends upon the other variable, from which it is concluded that each side must be a constant. This is the most vital thing. The last message is there. So idea is a separation of variables. So what we do? The partial differential equation with this idea of the solution. What the solution is there? Dependent variable is going to be expressed as a product of unknown functions of independent variables, separately, independently. If one function, assume that, is function of the variable x being an independent variable, then the other one is going to be function of the variable y, another independent variable. So unknown functions are there, depends on only one of the independent variables. Then further, we see that with this idea, with this message, the partial differential equation is going to be expressed, is going to be written in such a way that one side of the equation is purely dependent upon one variable, while the other one is going to be dependent upon the remaining variable. No, two sides are there with separation of variables. Variables are nicely separated on either side of the equality sign. Since they are equal to each other, their common value can't be the function of x or the function of y. So what we do eventually, we will assume that both sides must be identically equal to a constant value, because left hand side, if it is constant, a function of the variable x, the right hand side is function of y, and they're equal to each other. What is their common value? It is going to be a constant value. So we will look into this. By the repetition of this, the given partial differential equation reduces to 2. Are more than 2 ordinary differential equations, each one involving one of the independent variables. Solving these ordinary differential equations, the unknown functions can be determined. That's what we initially assumed with the solution. It is going to be product of unknown functions. So partway through the journey, we have to obtain those unknown functions by solving ordinary differential equation. Remember, we start off with the partial differential equation. They've been reduced or described into ordinary differential equations. From the ordinary differential equations, we will find unknown functions. And then the principle of superposition can then be used to find the actual solution of the given partial differential equation. So look into the Demonstration, we look into the illustration of this method of separation of variables by taking few examples. So idea is it, we will start with the assumption of unknown functions. Product of them is going to describe the solution. So this is what the starting point is. Take an example. By the method of separation of variables, we have to solve the following partial differential equations. So you see that u, it's a partial derivative with respect to x. It's a partial derivative with respect to y, is it? So one can imagine behind the scene, u is going to be function of the variable x and y. So we take the first part, ux plus uy is equal to 0. But the starting point with this method, it's an assumption about the solution. The dependent variable in the example u, that one, is going to be expressed as a product of unknown functions, each of which depends upon only one of the independent variable. So what we do? We assume that u of xy is equal to product of two unknown functions, capital X, capital Y. What is capital X? Purely function of the variable x. What is capital Y? Purely function of the variable y. But for simplicity, we just write it down, capital X times capital Y. Understandably, behind the scene, x is going to be a function of this variable x, small x, and capital Y is going to be function of small y. So this is the assumption. We assume that the solution of every partial differential equation by using the method of separation of variables is going to be described as the product of unknown functions. So we have two independent variables. So we take the product of two unknown functions, capital X and capital Y. They purely depend upon x and y respectively. No, we look into the mood, the description or the formulation of the given partial differential equation. What we need to see, that what type of the derivatives are involved. So we have derivative of u with respect to x. We have derivative of u with respect to y. Of course, they are partial derivatives. So this is going to be assumption being the solution of that equation. So take its partial derivative with respect to x. So capital Y is purely function of the variable y, whereas capital X is going to be function of the variable x. So if you differentiate partially with respect to x, so it's going to be x prime. We held fixed capital Y because it is going to be function of the variable y. And once we differentiate partially with respect to y, capital X is going to be held fixed because it is going to be function of the variable x. So and derivative of capital Y with respect to y is going to be y prime. So this is how we have ux and uy from equation number 30. The given equation is that one. So plug in the expression for ux and uy in that equation. So we will be having this expression. What is capital X? It's the rate of change of capital X with respect to small x. Y prime is the rate of change of capital Y with respect to small y. That's the type of graphical error. So capital Y is the instantaneous state of change of capital Y with respect to y, and capital X is the x prime is going to be the instantaneous state of change of capital X with respect to small x. So we have this equation now from the given partial differential equation. So separating variables, the same idea. So once we separate variables on either side of the equality sign, purely left-hand side is going to be function of the variable x, because x, capital X, depends upon the values of the variable small x. Same is the case with x prime. And the right-hand side is purely function of the variable y. Now you see that we have to implement this idea that each side must be a constant. Why so? We see that left-hand side is purely function of the variable x, right-hand side is purely function of y, and since they are equal to each other, their common value cannot be function of x either, or the function of the variable y. If it is the case, you see that then the left-hand side is purely function of x, but the right-hand side is purely function of y. So this is only possible if both sides are equal to some constant. That's why we describe it here. Since the left-hand side of the above equation depends upon x, whereas the right-hand side depends upon y explicitly, and on top of that, since they are equal to each other, their common value cannot be function of either x or y. Yes, because the left-hand side is purely function of x, but not the right-hand side. The right-hand side is purely function of y, but not of the variable x. So their common value cannot be a function of either x or y, and must therefore be a constant value. This is the only possibility. So we assume it as C, for example. So they are equal to each other, and their common value is a constant value. So separate them. The left, extreme left with C. From there, it will turn out to be x prime minus cx equal to 0. Take this equality sign. Y prime upon y is equal to C. So this could also be written as y prime plus C times y equal to 0. No, with the assumption of the solution of partial differential equation as the product of unknown functions, we eventually are talking about this aspect. The given partial differential equation reduces to two or more than two ordinary differential equations involving one of the independent variables. So you see that, yes, so we have two ordinary differential equation. The first one depends upon x. The second one is purely depends upon the variable y. It's a very simple one, very, very simple one. First order differential equation. In the dependent variable capital X, independent variable small x. The second one is first order differential equation in the dependent variable capital Y, independent variable small y. So we know the solution. We got an idea, enough idea about the solution of these kind of equations. So the solution of this equation would be capital A times e raised to power c x. Capital X is going to be a function of small x. And from the second equation, capital Y being the function of small y would be equal to that, where A and B are arbitrary constants. C is that constant value. So with the assumption that U is going to be solution of this equation in that particular fashion expressed as the product of unknown function. So finally, we have an expression for capital X. We have an expression for capital Y. So plug in capital X, capital Y as an expression of X and Y, small x, small y respectively. So plug in capital X, capital Y, simplify as much as you can. Yes, the combination of two unknown, two arbitrary constants could also be replaced by another arbitrary constant k. So yes, eventually we will be having this solution. U of xy is equal to k times e raised to power c times x minus y, being the function of x and y. So this is the solution. Nothing complicated, but the main thing is there you need to pick the idea. There are only few steps to pay attention. The very first thing every time with the method of separation of variables, our assumption would be something like that. Based upon the formulation of the given partial differential equation, we will take its partial derivatives. So you see that ux is there, uy is there. So we obtain ux and uy from that assumption. Plug in those derivatives in this equation. From there, we will obtain ordinary differential equations. From the solution of those ordinary differential equations, we finally find the expressions for those unknown functions. So because capital X is unknown, capital Y is unknown. So once we simplify that, ux plus uy equal to 0, eventually we have capital X and capital Y. So plug in over here in that equation number 30. So it will take you to the solution of that equation, because this is the assumption. We assume this and eventually we find capital X and capital Y to describe the solution. So we see that yes, this is going to be a solution. How do we justify this one? How do you check that whether it's a solution of the given equation or not? So you need to satisfy this equation with all sort of partial derivatives identically. So take its partial derivatives with respect to x and y, plug in this equation. If the equation is satisfied, we are happy. Yes, this is going to be the solution. If you look into the second part, again, you need to take start with the same assumption. U of xy is equal to capital X times capital Y. Now, depends upon the configuration, depends upon the formulation of the partial differential equation. You have to obtain those partial derivatives from this assumption. So you see that in the first case, we had to obtain partial derivatives of u with respect to x and y. No, we have to obtain the second partial derivative, mixed derivative is there, with respect to x and then with respect to y. Here you go with the idea. uxy is equal to u. So u of xy is equal to capital X times capital Y. Same assumption. We take start. If you look into the given partial differential equation, we will be having u. Yes, u is equal to capital X, capital Y. We also need uxy. So I look into the mixed derivatives with respect to x first, and then with respect to y. So eventually you will be having x prime, y prime. So plug in u from this equation, uxy from here in that equation. So it will be something like that. What is capital X prime? It's an instantaneous rate of change of capital X with respect to x. Capital Y prime is the instantaneous rate of change of capital Y with respect to small y. So if we look into this equation, by separating variables, we will be having function of x, purely function of x, the left hand side, purely function of y, the right hand side, and then with the same argument. The left hand side is purely function of x, the right hand side is purely function of the variable y, and since they are equal to each other, so their common value cannot be either x or y, and therefore must be a constant value. So you will assume that they are equal, since they are equal to each other, and their common value is going to be constant value c, and then further you proceed in that fashion. You will be having to ordinary differential equation, get the solution of those ordinary differential equations, and from there you will find the solution. Number 8. Number 8. No, please. Otherwise, I do it. All right. So this is all. The idea is that we extend our journey with the method of separation of variables to solve boundary value problems. So we know that, remember, boundary conditions must be there. If there is a function of only one independent variable, always one single equation is going to describe initial condition. In the case of function of one variable. But remember, when we have a function of more than one variables, there could be one condition, and even then the problem is going to be a boundary value problem. Remember, in this case, for example, u is a function of variable x and y. There is one unique value to the variable x. But what about the values of y? So we have no certain value of y. So we could have as many as you can imagine. So this is all. We can describe this problem as boundary value problem because we do not have one unique value to the variable x as well as to the variable y. So mathematical formulation is there. Together with the conditions, we say that this is going to be a boundary value problem. One condition is there, but because of more than one independent variables, no certain value to one of the independent variables, we say that this is going to be boundary value problem. So we need to move further from the solution, which is going to be a general solution, to a particular one by utilizing the given condition. So pretty much the same idea. For this particular equation, assume that u of xy is equal to capital X, capital Y, being the solution of this equation. Now, what we see in this equation, we have the involvement of partial derivatives of u with respect to x and y. So take partial derivatives of this equation with respect to x and y. Plug in those partial derivatives in the given partial differential equation. Ux is equal to 4 times uy. So ux is going to be replaced by x prime y, and uy is going to be replaced by capital X times capital Y prime. So plug in there, and you will be having this equation. Then the very next step is going to be the separation of variables. Separating variables, we will be having x prime upon 4x is equal to capital Y prime upon y. And the same argument, every time you need to look into this wording. Since the left-hand side is purely function of the variable x, the right-hand side is purely function of the variable y, their common value cannot be a function of either x or y, and must therefore be a constant value. So what we assume, say it is going to be C. So they are equal to each other and the common value is going to be C. So take this expression equal to C once, and from here you will be having this equation. Take that one is equal to C. From there you will be having this equation. So in this way we have two first order ordinary differential equations. If you look into the solution of this one, pretty simple. You will be having capital X as a function of small x. From here, capital Y as a function of small y. Respectively, they are solutions to this equation and that equation respectively. A and B are arbitrary constants. So what we do, we started off with this assumption. Finally, we got an expression for capital X and capital Y. So plug in those expressions for a capital X and capital Y in the given partial differential equation. So we will be having an expression of this nature. The simplified, because eventually the combination of these two arbitrary constants is going to be replaced by another constant. And this is going to be the simplified. It is more elegant, more nice to replace A times B by K, because they are arbitrary constants, could be replaced by another constant. So it's the solution, but the solution is going to be a general solution. So we are interested to find a particular solution from this equation by obtaining the values of those arbitrary constants, capitals K and small c, for example. So how we do that? You need to apply the condition. So in the first case, condition is this one. Condition is this one. So apply this condition. What the condition is? U of 0y means add x equal to 0 for every value of y, u is equal to this one. So u is equal to k times e raised to power c times 4x plus y. So replace x by 0 over here. So it will turn out to be cy in the exponent of e. To the left hand side, u of 0y, and u of 0y is equal to a times e raised to power minus cy. So plug in u of 0y to the right hand side, x by 0, y is still there. No, they are equal to each other. And if you remember from assumed knowledge that one term is going to be described as the combination of three elements. What are those elements? There must be a coefficient, base is there, and then the exponent. Since they are equal to each other, so every element is going to be identical. They are equal to each other only if their coefficients, their base, as well as their exponent are equal to each other. So if you do compare them, means 8 is equal to k, e is equal to e, minus 3 is going to be c. So do compare them. Eventually we will be having k is equal to 8 and c is equal to minus 3, and that's what we were looking for. So take the value of k and c, plug in over here. So this is going to be a particular expression free from arbitrary constants. 8 and 3, 4, they are not arbitrary constants. Remember, they are certain. So this is going to be the solution of the given boundary value problem. So this is how we got an idea. Got an idea about the technique, most viable technique available in the literature for solving partial differential equations, known as separation of variables. All right, before we move on, I generate a poll for attendance purpose. UP Pro. So it's 29th of July 2020 and we are interested to see health of the present. So here you go with the poll. So poll has been created for attendance purpose. All right, we move on. A few examples are there. Take those examples as homework based upon the description of different topics been discussed inside partial differential equations. So the first bunch of examples about obtaining partial differential equation, and we know that partial differential equations could be obtained, could be formulated by eliminating arbitrary constants, or they could also be obtained by eliminating arbitrary functions. So if you look into the first bunch of examples, it is asked to obtain the partial differential equations by eliminating arbitrary constants from the following relations. What type of the relations are there? They are relations of the dependent variable and independent variables involving certain arbitrary constants. You see that u and xy. It's a relation between variables, u being dependent, x and y independent. On top of that, a and b being arbitrary constants. So you need to eliminate those arbitrary constants. You got an idea. How do we eliminate them? Based upon the number of arbitrary constants, how do we form the corresponding partial differential equation? We started off with this idea, formation of partial differential equations by eliminating arbitrary constants. I mean, you need to look into the number of arbitrary constants and the number of independent variables. Either they are equal to each other, arbitrary constants less than the the number of independent variables or arbitrary constants are more than the number of independent variables. So these are the scenarios over there. Second bunch of examples, we need to obtain partial differential equations by eliminating arbitrary functions. So in the first case, you need to play around to get rid of f. In this case, f is going to be a function of x and y. So the expression is there 1 upon x plus natural log of y. So you need to eliminate f. From here, again, f is a function of x and y. You need to eliminate f and g from example number 3. 2 arbitrary functions are there to be eliminated. Same is the case with example number 2 and part number 4. You have to eliminate f and g. Next example, show that u of x, y is equal to x times f of 2x plus y is a general solution to this equation. So pretty general thing is there. Generally, when do we say that a relation between dependent and independent variables is going to be a solution? So we know that if the relation and its derivatives, they all simultaneously satisfy the given differential equation. In this case, it's a partial differential equation, so u is going to be a function of x and y. Not only u, but its partial derivatives with respect to x and y, they must satisfy this equation. So many ways you can look into the satisfaction of this equation. One way, take this u to the left hand side, or everything from left hand side to the right hand side equal to 0, and plug in u, ux, uy over here, and then show that yes, 0 is equal to 0. For some time, you could also do that in a way that you replace ux here, uy here, and then simplify the left hand side. Once it is identical to the right hand side, it is justification. It will justify, yes, u is going to be the solution. On top of that, we have to find a particular solution satisfying u of 1y equal to y squared. So apply this condition. To find a particular solution, u of 1y means for any sort of value of y, but for one particular value of x as 1. So next example, we need to show that u of xt e raised to pi minus 8t sine of 2x is a solution to the following initial boundary value problem. Remember, we know the initial value problem and the boundary value problem. If the problem is there together with initial conditions, it is known as initial value problem. A problem together with boundary conditions is known as boundary value problem. Not the combination of them could be there, as we see in this example. Not only the initial condition is there, but also the boundary conditions are there. For the starting value of t, 0, condition is there. But since we are not sure about the values of t, on top of that, two different values are there for the variable x. So boundary conditions are there. Phenomena is there to describe in the form of partial differential equation. Boundary conditions are there. Initial condition is there. So this whole thing, mathematical formulation, together with boundary conditions and initial condition, it is going to be initial boundary value problem. So you need to show that u of xt is equal to e raised to power minus 8t sine of 2x is a solution to this initial boundary value problem. Solve the following partial differential equation. So many ways we got an idea about the solution of partial differential equations. Many ways we can handle them. So you see that we have three partial derivatives, third order partial derivative. 3 times it's been partially differentiated, twice with respect to x, and on top of that, once with respect to y. So one of the viable options is to integrate them. Both expressions to the left hand side, to the right hand side, first with respect to y, and then twice with respect to x. Integrate them. And eventually you will be having this solution, u of xy as an expression to the right hand side as a result of integrating both sides. Partially with respect to y, derivatives are there with respect to x, so you need to integrate with respect to y initially. So arbitrary constant is going to be a function of the variable x, remember. Then twice integrate with respect to x. So once you integrate with respect to x, constant of integration would be function of the variable y, the other variable. Next bunch of examples. Classify the following partial differential equations according to the type. What the type is there? If you remember, we know the generalized representation of any linear homogeneous partial differential equation of order 2. So this is going to be that. Coefficient of uxx, coefficient of uxy, coefficient of uyy, coefficient of ux, uy, and then of u. So a, b, c, d, e, f. The dominant coefficients are going to be coefficients of highest derivatives, means second derivatives. We have 3 of them. Double derivative with respect to x, mixed derivative of u with respect to x and y, double partial derivative of u with respect to y. So A, B, C, they play vital role because they are the dominant terms, coefficient. Dominant terms in a way of highest derivatives. So based upon this expression, B square minus AC, so BAC, BAC, they are partial derivatives of the highest derivatives in this second order partial differential equations. So based upon the value, explicit value being negative, 0 or positive, we say that the equation is going to describe the geometry as ellipse. If this value is negative, parabola. If this value b square minus AC is equal to 0, and hyperbola if this value is positive. So this is all based upon this discriminant. You need to classify these examples. So A is there, B is there, C is there. So take A, B, C, and then C. But also sometimes you need to keep an eye on this very vital remark. A partial differential equation may be of elliptical shape in one region of the plane, of parabolic shape in another region, and hyperbolic shape in yet another region. For example, if b square minus AC is equal to y, for example, y is a variable, it's not a constant value. So then we will have to look into 3 different scenarios when y is positive, We know that it's above the horizontal axis. When y is equal to 0 on the horizontal axis, and when y is negative, less than or below the horizontal axis. So you will be having three regions over there. Above the horizontal axis, on the horizontal axis, it will go side by side, and below the horizontal axis. So you will be having three regions over there. So in case if b square minus ac is equal to y, for example, and then from there, you will see that yes, one equation is there, but it is going to be represented as an ellipse, parabola, and even hyperbola in different regions. So you also have to look into this vital note. It might be the case when we talk about part number 4, because variables are there. So being the coefficient, so there might be a chance. Next bunch of examples using the method of separation of variables, solve the following partial differential equations. So we got an idea in our today's lecture. How do we look into the solution? Every time with this method of separation of variables, we take start with assumption. So depends upon the number of independent variables. So U is going to be described as the product of unknown functions. Since U is function of x and y, so U of x, y would be equal to capital X of x, capital Y of small y. And that's the starting point. We will take start from here based upon the scenario. So how many partial derivatives are there? What type of the partial derivatives are there? So you need U, capital X, capital Y. You also need Ux, Uy. Plug in over here, and then with the help of separation of variables, there will be ordinary differential equation. You will see that in the second example, U is there, and the mixed derivative is also required, and then separation of variables will take you ordinary differential equations. Using the method of separation of variables is an extended version. Not only we have to find the solution, but also we need to look into the implementation of boundary conditions. So boundary value problems. And that's it. We got an idea so far about the formulation by eliminating arbitrary constants, arbitrary functions, different way to find the solution, how do we justify the solution, classification, and then one of the most prominent technique to find the solution of partial differential equations known as method of separation of variables. So this is all. We have an idea so far about the partial differential equations. How do we handle them? All right, so for today's lecture, that's it. Ample of time is there, so we can handle. If there are certain queries about the previous lectures or the one that we have discussed in today's lecture,